To discuss the AC series circuits. So let us discuss the RL series circuit. We consider an RL series circuit as shown in the given figure. We have applied an AC voltage source across the series combination of the resistor and inductor. There is a flow of AC current in the circuit, and this AC current results in a voltage VR across the resistor and a voltage VL across the inductor. If we apply KVL to this loop, according to KVL, the sum of the voltage rises in this loop will be equal to the sum of the voltage drops. In other words, the algebraic sum of all the voltages in a specific direction in a loop is always equal to 0. So the voltage across the source will be equal to voltage across the resistor and voltage across the inductor. So we apply KVL to the given simple series circuit, and according to KVL, the AC voltage across the source is equal to the AC voltage across the resistor and the AC voltage across the inductor. So we assume that the equation for the current in this series circuit is known, and we are going to find out the equation for the AC voltage across the resistor and the AC voltage across the inductor and the AC voltage across the source. So the time varying equation for the alternating current in this series circuit is given by this equation. The AC current in this series circuit is equal to Im sine omega t. So we assume that this equation for the current is known, and we are going to find out the voltage across the resistor, the voltage across the inductor, and the voltage across the source with the help of this current. So the voltage across the resistor will be equal to IR. We are going to consider the voltage across the resistor after the current slide. We consider the waveform for the current in this series circuit. This is the waveform for the AC current in this series circuit. We have considered one complete cycle of this AC current. Here is the positive half cycle, and here is the negative half cycle of this AC current. We know the magnitude as well as the direction of this current changes with respect to time. So if this is the direction of the current during the positive half cycle, then definitely the current, this will be the direction of the current in the negative half cycle. Anyhow, we are going to find out the voltage across the resistor, and the voltage across the resistor is equal to IR we put the value of the current in this equation. So PR will be equal to IMR sine omega t. So here is the maximum or the peak value of the AC voltage across the resistor. IMR indicates the peak value or the maximum value of the AC voltage across the resistor. So here is the maximum or the peak value of the AC voltage across the resistor. And we consider the waveform for the AC voltage across the resistor. Here is the waveform for the AC voltage across the resistor. We have taken the voltage across the resistor along vertical axis, omega t along horizontal axis, and the peak value of this AC voltage is IMR. So you see, we consider the waveform for the AC current. Here is the waveform for the AC current, and here is the waveform for the AC voltage across the resistor. We compare the waveforms as well as the equation. You see, we can write down the equation for the voltage across the resistor in this form as well. We have omega t plus 0, omega t plus 0, and this 0 is known as the phase angle of the voltage across the resistor. So the phase angle of the voltage across the resistor is 0. Similarly, if we consider the equation for the AC current, we have the maximum value of the current into sine of omega t plus 0. We can write down the equation for the AC current in this form as well. And you see, the phase angle of the AC current is 0. So the phase angle of the voltage across the resistor as well as the phase angle of the AC current in this series circuit is 0. So we say that the voltage across the resistor is in phase with the current. The voltage across the resistor is always in phase with the current because the phase angle of this voltage as well as this current are 0. So there is no phase difference between the voltage across the resistor and the current in the resistor. The voltage across the resistor is always in phase with the current. We can find out the voltage across the inductor with the help of this particular equation. The voltage across the inductor is equal to L di by dt. And if we put the value of this AC current in this equation, we get the AC voltage across the inductor of this series circuit. The voltage across the inductor will be equal to Im XL into cos of omega t. And here is the peak value or the maximum value of the voltage across the inductor. So this value is the maximum value are the peak value of the AC voltage across the inductor. And we can write down this equation in this form as well. The voltage across the inductor will be equal to the maximum value of the current into XL into sine of omega t plus 90. So we can write down this equation in this form as well. Well, we plot this voltage with respect to omega t. We consider the waveform of this voltage. So here is the waveform for the voltage across the inductor, and the voltage across the inductor starts from minus 90 degree. So this is the waveform for the AC voltage across the inductor. If we consider the equation for the current, and if we compare the equation for the current with the equation for the voltage across the inductor, you see here is the equation for the current. The AC current is equal to the maximum value of the current into sine of omega t plus 0. So the phase angle of this AC current is 0, while the phase angle of this AC voltage is plus 90 degree. So there is a phase difference of 90 degree between the voltage across the inductor and the current in the inductor. In other words, the voltage across the inductor leads the current by 90 degree, or the current in the inductor lags behind the voltage across the inductor by 90 degree. So you guys can see that there is a phase difference of 90 degree between the voltage across the inductor and the current. Now what we do, we consider the voltage across the source. We applied KVL to the given circuit, and according to KVL, V S will be equal to VR plus VL. The voltage across the resistor in accordance with KVL is equal to voltage across the resistor plus voltage across the inductor. And the voltage across the resistor is equal to IMR sine omega t. And the voltage across the inductor is IM XL cos omega t. So we put the values of VR and VL in this equation. If we put the values of the voltage across the resistor and the voltage across the inductor in this equation, we get this particular equation. So the voltage across the source is equal to IMR sine omega t plus IM XL cos omega t. We can find out the instantaneous value of the AC voltage across the source with the help of this particular equation. So you guys can put the value of time on the right hand side, and you guys can find out the voltage across the source at any time, at any instant. Now let us consider the equation for the AC current. So we consider the equation for the AC current. Here is the equation for the AC current. You see, this is an AC current, and this equation can be written as this AC current is equal to the maximum value. So the AC current has a maximum value, it has the sign terms, and then it has a phase angle which is equal to 0. So we can write down, you see, the equation for the current in this form. You see, the AC current varies sinusoidally with respect to time. Here is the maximum value of the AC voltage, and here is the phase angle of the AC. Here is the maximum value of the AC current, and here is the phase angle of the AC current. So the AC current has a maximum value as well as a phase angle. Similarly, we consider the voltage across the resistor. Here is the equation for the voltage across the resistor, and this equation can be written as omega t can be written as omega t plus 0. So this is an AC voltage which varies sinusoidally with respect to time, and here is the maximum value of this AC voltage, and here is the phase angle of this AC voltage. So the AC voltage has a maximum or a peak value as well as a phase angle. Here is the maximum value of this AC voltage, and here is the phase angle of this AC voltage. So AC voltage will have a proper maximum value and a proper phase angle. Let us consider the voltage across the inductor. Here is the voltage across the inductor, and we can write down this voltage across the inductor in this form as well. The voltage across the inductor is equal to Im into XL, and this quantity represents the maximum value of this AC voltage, and then we have sine of omega t plus 90. So we can write down this equation in this form as well. So this is an AC voltage across the inductor, and this AC voltage has a proper maximum value. So here is, let me write down the maximum value of this voltage once again. Here is the maximum value of this voltage, and here is the phase angle of this AC voltage. So the maximum value of this AC voltage is IMXL, and the phase angle of this AC voltage is 90 degree. So what we conclude? We conclude that the AC voltage varies sinusoidally with respect to time, and the AC voltage has a maximum value and a proper phase angle. The phase angle might be 0, it might be 90 degree, it might be less than 90 degree, but it has a phase angle. So now if we consider the equation for the source voltage, which is an AC voltage, so here is the instantaneous equation for the AC voltage. We can find out the instantaneous value of the AC voltage with the help of this equation at any point of time. But this is an AC voltage, and we know that the AC voltage varies sinusoidally with respect to time. This AC voltage will have a maximum value and a phase angle. So there is a problem with the right hand side of this equation. And what is the problem with the right hand side of this equation? The problem with the right hand side of this equation is that the right hand side of this equation does not give you the maximum value of this AC voltage, and it does not give you the phase angle of this AC voltage. So we are going to write down the generic equation for the AC voltage. Why? Because the AC voltage varies sinusoidally with respect to time. So this voltage will have a maximum value. Let me represent the maximum value of this AC voltage by Vm. This voltage varies sinusoidally with respect to time, so it will have a sine term. So it will have a sine term, and this voltage will have a phase angle. This voltage will have a phase angle. So let me represent the phase angle by theta. So this will be the general equation for the AC voltage. We represent the maximum value of this voltage by Vm, and we represent the phase angle of this voltage by theta. So we can find out the source voltage with the help of this particular equation. We can find out the voltage across the source with the help of this particular equation. So we consider the general equation for the AC voltage. We know that the AC voltage varies sinusoidally with respect to time. This voltage has a maximum value which is represented by Vm, and it has a proper phase angle which is represented by theta. So this is the general equation for the AC voltage across the source. But you see, the maximum value of this AC voltage is unknown so far. How to find out the maximum value of this AC voltage? Similarly, the phase angle of this AC voltage is unknown yet. So how to find out the phase angle of this AC voltage? Now what we do, we consider the original circuit. So let me consider the original circuit over here. We have a series combination of a resistor, and we have a series combination of a resistor and an inductor, and we have applied an AC voltage across this series combination. So the resistance of the resistor is RL, the inductive reactance of the inductor is XL, and here is the AC voltage. The AC voltage across the source is represented by Vs, and there will be an AC current in this particular circuit. So we know that there are two circuit elements. There are two passive circuit elements in this particular series circuit. We have the resistor, and this resistor offers this much resistance to the AC current. Similarly, the inductor offers this much resistance to the flow of this AC current. So the resistance opposes the AC current and the inductor opposes this AC current. So we can say that this AC circuit will oppose the flow of AC current. It will oppose the AC current. So what we do, we assume that the total resistance of this series circuit is represented by Z. So we replace the series combination of these two circuit elements by a single passive circuit element, and we assume that the resistance of this single passive circuit element is represented by Z. Z is known as impedance. So Z is basically equal to the total resistance of this series circuit. So what we do, we replace the series combination of the resistor and inductor in this particular circuit by a single circuit element which is represented by a box, and we assume that the impedance or the resistance of this single circuit element is equal to the total resistance of our original series circuit, right? And we apply the same voltage across this single passive circuit element. So there will be a flow of AC current in this series circuit, and this current will result in a voltage drop across the across this passive circuit element. If we apply KVL to this loop, according to KVL, the voltage across the source will be equal to the voltage across this impedance, the voltage across this element, the voltage across this passive circuit element. So Vs will be equal to Vz. So if we apply KVL to this loop, according to KVL, the voltage across the source will be equal to the voltage across this passive circuit element. In other words, the maximum value of the AC voltage across the source will be equal to the maximum value of the voltage across the passive circuit element, which is represented by Z. We know that the maximum value of the voltage across the resistor is equal to the maximum value of the current into resistance of the resistor. This is how we calculate the maximum voltage across the resistor. Similarly, the maximum voltage across the inductor is equal to the maximum value of the current multiplied by the resistance of the inductor, which is known as inductive reactance, which is represented by XL. So this is how we calculate the maximum voltage across the resistor, and this is how we calculate the maximum voltage across the inductor. Similarly, we can find out the maximum voltage across this passive circuit element if the maximum value of the current in this passive circuit element is known and the resistance of this passive circuit element is known. So the resistance of this passive circuit element is represented by Z. So the maximum voltage across the source or this passive circuit element will be equal to the maximum value of the current into Z. So this is how we calculate the maximum value of the AC voltage across the source, right? And what we do, we put this value of the maximum value of the AC voltage in this equation. You see, this is the general equation for the source voltage, and we know that here is the maximum value of the source voltage, which is unknown yet, and we replace this maximum value of the source voltage by the maximum value of the current into Z, where Z is known as impedance, which is the total resistance offered by our series circuit to the flow of AC current. So this is the impedance of our series circuit, or the total resistance of our series circuit. So we replace this Vm by Imz. So let us replace Vm in this equation by Imz. So you see, we replace Vm in the equation for the source voltage by Imz, and so this is the maximum value of the source voltage, and here is the phase angle of the source voltage. You see, the maximum value of the current in this equation is known. So the maximum value of the AC current is known, but the impedance of this series circuit is unknown so far. We don't know what will be the total resistance of our series circuit, what will be the impedance of our series circuit. We need to find out the total resistance of our series circuit. We need to find out the total impedance of our series circuit. Similarly, theta is unknown. We don't know the phase angle of this source voltage so far. So what we need to do, we need to find out the impedance of the series circuit and the phase angle of this AC voltage. All right. So let us focus on these two stuff. We focus on the impedance of our series circuit and the phase angle of the source voltage. What we do, we expand this term. We know that sine of omega t plus theta is equal to sine of omega t cos theta plus cos omega t sine theta. So we expand this particular term. If we expand this term, the voltage across the source will be equal to, so we expand sine of omega t plus theta. If we expand sine of omega t plus theta, we will get sine omega t cos theta plus cos omega t sine theta. And then if we rearrange the equation, the voltage across the source will be equal to Imz cos theta sine omega t plus Imz sine theta cos omega t, right? And we can find out the voltage across the source with the help of this particular equation, and we can find out the voltage across the source with the help of this equation as well. Let me show you another equation which we have already discussed. Okay, So we can find out the voltage across the source with the help of this particular equation, or with the help of this particular equation. We derived this equation now. The voltage across the source will be equal to IMZ IMZ cos theta sine omega t plus IMZ sine theta cos omega t. So we can find out, you see, the voltage across the source either with the help of this equation or this equation. You see, if we compare this equation, then R will be equal to Z cos theta. Similarly, XL will be equal to Z XL will be equal to Z sine theta. So XL will be equal to Z sine theta. So R is equal to Z cos theta and XL is equal to Z sine theta. So basically we compare these two equations. If we compare these two equations, then R is equal to Z cos theta and XL is equal to Z sine theta. So what we do, we take square on both sides of this equation and then we add it. So we take the squares on both sides and we add them. So we have R square, which is equal to Z square cos square theta, and we have XL square, which is equal to Z square sine square theta. So if we add these two equations, we get R square plus XL square, which will be equal to Z square. So basically on the right hand side, you see, on the right hand side we get Z square into sine square theta plus cos square theta, and we know that sine square theta plus cos square theta is 1, so we get Z square on the right hand side. So Z square will be equal to R square plus XL square, or Z will be equal to under root R square plus XL square. So we can calculate the impedance of this series circuit with the help of this particular equation. Similarly, if you want to find out theta, so for the calculation of theta, we divide this equation by this equation, right? So if we divide this equation by this equation, we will get tangent theta, which will be equal to XL by R. So we get tangent theta, and tangent theta is basically equal to XL by R, and theta will be equal to tangent inverse XL by R. So we can find out theta with the help of this particular equation. So as far as the impedance is concerned, we can calculate the impedance of the series circuit, and we can calculate the phase angle of this the phase angle of this AC voltage. We have already derived this equation. This is the instantaneous value of the power taken by the resistor, which is equal to Im square R into sine square omega t. Similarly, we have already derived the power taken by the instantaneous power taken by the inductor, which is equal to Im square XL by 2 sine of 2 omega t. So we have already discussed these two equations. So the total power taken by the entire circuit, which is basically equal to the total power supplied by the source. We know that according to the law of conservation of energy, the power supplied by the source will be equal to the power taken by the entire circuit. So the power supplied by the source will be equal to PR plus PL. If we put the value of PR and PL on the right hand side of this equation, we get this particular equation. So we can calculate the total power supplied by the source with the help of equation number 3.59. We calculate the average value of the AC power supplied by the source. So the average value of the AC power supplied by the source will be equal to PR plus PL. We know that the average value of the power taken by the inductor is 0. So PS will be equal to PR, and we know that PR is equal to I square R. So this is how we calculate the power supplied by the source. So let us do a numerical question. Here is the equation for the AC current in this series circuit. The resistor of this series circuit is 3 ohm. The inductive reactance is 4 ohm, and the equation for the current is known, that is 10 under root 2 sine of 100 pi t. So the equation for the current in this series circuit is known. We calculate the impedance. We will derive this equation later on. Anyhow, the impedance of this series circuit will be equal to 3 plus J4. This impedance is in rectangular form. If you want to convert it into polar form, the magnitude of this impedance will be 5. The angle will be 53.1. The maximum value of the current is 10 under root 2 ampere. The angular frequency of the source is 100 pi radian per second. So this is the data which is given in the circuit diagram, and we calculate VR. So we calculate VR with the help of this particular equation. We know that VR is equal to IMR into sine of omega t. You see, Im is known, resistance is known, and omega is known. If we put the values on the right hand side of this equation, the voltage across the resistor is equal to 30 under root 2 sine of 100 pi t. The voltage across the inductor is calculated with the help of this particular equation. So the maximum value of the current is known, the inductive reactance is known, the angular frequency is known. So you put the values on the right hand side. The voltage across the inductor is equal to 40 under root 2 cos of 100 pi t. This is the AC voltage across the inductor. Similarly, the AC voltage across the source, for the AC voltage across the source, we use this particular equation. We have the maximum value of the current, which is 10 under root 2. The magnitude of the impedance, we have already calculated this impedance, which is 5 theta. So we have already calculated this theta. Theta is with the impedance. You see, this impedance is basically equal to 5 with an angle of 53.1. So this 53.1 is theta. So Vs will be equal to 50 under root 2 sine of 100 pi t plus 53.1. In order to calculate the instantaneous power taken by the resistor, we use this particular equation. We put the values on the right hand side, so we get the power taken by the resistor. Similarly, the power taken by the inductor can be calculated with the help of this particular equation. We put the values on the right hand side and we get the power taken by the inductor in this particular case. We will do a few more numerical examples later on.